the signal is not, it seems nearly random. But at the same time, there's information in it regarding the strength of contraction. So if I want to estimate the strength of contraction, as someone said, you can look at it and you can get some idea. But that's not enough. I want to be a bit more exact with it. I want to do it computerized. How will I do it?
Strength of contraction.
Correct.
In the force signals has to be converted in terms of force. Right.
An estimate of force.
Yes. We need to use these signals to estimate the force.
Correct. Question clear? Huh? No? Okay. If I've got signals, random looking signals, like you are seeing, if there's greater amount of activity, the amplitude seems to be higher, the frequency seems to be higher. What will I do to estimate this? Can I measure the amplitude? Is that a possibility? Something simple. Can I do something? What is the simplest way you will do in order to estimate the force or the strength of the signal and thus the strength of contraction? Pardon? RMS value. Okay. Sure, but what feature will you use? So he has proposed RMS. Okay, so let's give us some names. So he says RMS. What do you say? So, okay, frequency. RMS is, when you say frequency, what do you mean? So are you talking about zero crossing? Is that what you're saying? Do you know what is zero crossing? Is that what you're saying? Or you're saying, and if you're having a frequency, you're not going to have one frequency in this, right? You're going to have a spectrum. So what are you going to measure in the spectrum? Are you going to measure the two-dimensional spectrum, where the peak is, where the lowest point is, highest point is, what? Mean, median, what? Pardon? So the area of under the curve of the spectrum. This area, this is frequency and this is whatever, x of f. Is that what you're saying, the area? So I take this, I integrate it. So instead of this, I now get like this. And then I integrate and take the integration of all of this. Is that what you're saying? Okay. So you are saying integral of the positive only. What do you call it? Positive only modulus. Is that what you're saying? Okay. Okay. Anything else? The latecomers will know the answer. Come on in front. Why are you sitting at the back? You're making me walk extra. Okay. Anyone else got the answer? Mean average value of what? Of the signal? Okay, so I'll take this signal and I'll take the mean average of this. Okay? So you say mean average. What do you mean mean average? Mean is average, right? So mean equal to average. Okay? Mean comma average. Okay? Anyone else? No. So no. What do we want? We want to get an estimate of the strength of contraction. For that, we are doing this. So yes, you were saying variance. So variance of the original signal, right? So he said mean, you say standard deviation of variance. Okay? What else? He's already said that. Thank you. He's beaten you to that. Okay? Huh? Power spectrum density. Okay? Everyone knows what these are? Do you know what's power spectrum density? You know? Okay? You don't know? Okay? Okay. Ma'am, please explain what is power spectrum density. Many people do not know. Wait, we'll give you a microphone. Where is your microphone gone? Oh, it's kept under lock and key. Oh, yeah, it is. It's not yep. We're going to get a tutorial on PSD.
So we'll take the estimate of the signal.
You don't have to look at me.
Yes, sir.
I think I know
Find your
PSD.
correlation, autocorrelation of the signal, what we have taken, and we'll apply Fourier transform to it to identify the frequency component present in that estimate range. So that we call it as power spectral density.
So you take the spectrum, and from the spectrum, what did you calculate?
What is the maximum spectral density it has? The range of frequencies it occupies.
So this is the frequency at which there is maximum?
Power. Which frequency has more power?
Yeah, so that is this one.
Yes.
Then I just take that frequency. So
power of the signal.
Power of the frequency.
Yeah.
Okay. I think we all now. What else? Any other feature that you understand? So let's have a look at what people have proposed. And I'm not saying everyone's right or wrong. Power spectral density, integral of the spectrum, integral of the absolute of the signal, RMS, something to do with frequency. No one told me what to do with frequency, but someone said frequency. So what you want a PSD is one measure of frequency, median frequency, etc. Could be any. Mean of the signal, variance of the signal, zero crossings. Yep. Anything else? Huh? Sample entropy. Various kinds of entropy. Sample. Okay. Fractals. Do you all know what's entropy? Yes? You studied entropy, the first lesson of physics in school. But you can still don't know it. That's okay. Huh? Entropy is the level of chaos, level of randomness in a signal. Everyone knows what's randomness, right? Okay? Guys, you know what's randomness? Yes? Okay? You know what's then entropy? If you put a gas in a container and leave it, what will happen to the entropy? Old thermal law, which we studied in physics, at least when that was my first lesson in school, physics. Remember? The entropy of a system increases, right? The randomness increases. Okay. Now, fractals. What are fractals? Again, a measure of complexity. It states that everything in the world which is fractal is basically definable by a very simple formula. Anything in the world. It is just how often you repeat it, it makes it more complex. Okay? That's called scalability. Anyway, we will not worry about that. So we can see that there are lots of measures. By the way, the only one which I think is wrong measure is this one, the mean. Can anyone say why? If I take a mean of this signal or mean of this signal, they both will give me 0. Right? So I will actually not get any information about the strength of the contraction. Okay. The most common one which is used among all of these, to my knowledge, is RMS. The reason, because RMS, you all know what's root mean square, right? You all, have you done it somewhere or the other in some form or the other? It's very easy to put it into a circuit. But it also has lots of problems. What do you think is the biggest challenge if I'm doing an RMS? What are the parameters that you need when you calculate root mean square? Anyone? When you calculate root mean square, what do you have to do? You have to tell the window size. Correct? Pardon? Yes, the window size. Pardon? Correct. So you are now assuming that within that window size, the information is remaining the same. If it is too small, it's changing too quickly, you don't understand. If it is too big, you're averaging the whole thing now. So if you take RMS of a person, of someone's EMG over one day, you'll only get one number. You don't know what the person did. All you know is that's some approximate idea that the person was maybe not sleeping or not dead. Right? Okay. So this is some of the things that you can try around with. And when you do that, you will get some answers with your own EMG. And you'll get a better estimate as to what kind of window size, what kind of parameters are relevant. I won't suggest go down the pathway of entropy, etc. right now, because they become rather complex to do. And you might be struggling at the stage of the whole thing. Try any of these and figure it out. Now, the other thing is, yesterday, you did some experiments and you realized you were getting some EMG. And when you were getting that EMG, you might find, did you experiment with electrodes on one side and the thing? Anyone made any observation on that? Try it out today when you're doing the analysis. What do you get? Now, when you are doing this, all of this, the other thing is going to be, we were talking about muscle fatigue. And yesterday, we were talking about that when muscle starts getting tired and fatigued, what happens? The inherent randomness in the stimulation starts decreasing. Because, okay, how many of you know ECG, heart rate? How many of you measure your heart rate on your phone or something like this, etc.? You do? How many of you do? I do. You do? Huh? You on your phone or your watch or something? How many of you have a smartwatch? I can see one there. Right? You use it for your heart rate and other things, right? So raise your hand. Say, come on. Why are you putting your hand down? Raise your hand. Right. How many do? Okay. 5, 6, 7. Is that all? Others don't use. You have a smartwatch, but you don't use it. Okay, it's analog watch. Okay, good. Now, when you do the heart rate, what do you know about it? That your heart rate is typically sitting at about 80, 70, depending upon how fit a person are you or you're not. You guys who went jogging and all, you must be keeping your heart rate, right? So when you jog, your heart rate goes up, otherwise it comes down. If your heart rate is absolutely still, 70, 70, 70, 70 all the time, is it a healthy sign or a bad sign? Okay, one vote says bad sign. Anyone says opposite? Anything? It should vary. Why? So if you're now sitting here, it should be the same. Do a quick search onto Dr. Google and ask, should heart rate, healthy heart rate, be the same or varying when resting? Resting heart rate. Okay. So this lady has Nuzi, right? Nizu. Nizu has found out that the heart rate should vary slightly. If it is very steady, in fact, that is generally a sign of near death. So heart rate itself is not considered important. What is important is HRV, heart rate variability. And why does heart rate variability matter? I'll give you a hint. If there is no variation in the heart rate, the same thing is happening all the time, that the heart can fatigue. Now think about the same thing in your muscle. If your muscle does the same contraction all the time, it will fatigue. So the muscle we studied yesterday, there's a recruitment pattern which goes on where something is recruited now, after a while that is relaxed and something else is recruited, right? You remember that? When it is fatigue, what is going to happen? That recruitment strategy is no longer possible because muscle should have enough to be able to do, but when it's become poor, it can't do anything. So you have to be rich in order to give, right? So now, back to here. When you've got the muscle which requires variability, so one of the reasons why he mentioned about entropy was that as you have more variability, you have more entropy. Your variance is higher, entropy is higher, right? So a healthy muscle will have a greater variance, greater entropy. When that starts reducing, that is a sign that there is fatigue. That's one simple thing of doing it. Whether it works or not work doesn't matter. But in theory, that is what we can say. When you have got a change in entropy or reduction in entropy, what other things you'd expect in the spectrum? When the magnitude will start going up. Okay? Pardon? The amplitude will start going up slightly. This frequency will start going down because they are becoming more and more together, less variability. Okay. So these are some of the things that happen, right? Which can happen. Now, what other things did we look at yesterday? We were talking about prosthetic control. When you're talking about prosthetic, what are you looking at? You are looking at something very fine. So, but the point is, how much exact can you measure your force? So that when I do that measurement, I can use it to control something, right? If I cannot do my exact measurement, then I could have a problem in controlling something. So the reason I asked you to do your activity at different levels and also to repeat it, because if you're using a device like a prosthetic device, you're not only using it once, you got to use it the whole day. So when you are doing it like that, it means that your device should be functional at all times. All right? So that is the other thing that you have to study is you have to see if the signal is that. By the way, what time is it? Is it coffee time? I wanted to change the topic after coffee. Okay. So, okay, so we have half an hour. Now, let's do one thing. Do you all have MATLAB with you? I asked you to get your laptops. Huh? Or you have Python? Okay. So under Python or MATLAB or whatever you get, I want you to play around with all of these. Forget about EMG for the moment. Just see whether you can, or forget about that too. Go on to Dr. Google or whatever and see what parameters do you need to calculate any of these things. What are the parameters that will get influenced by this? Okay, check. We've now spoken about lots of these parameters, right? Lots of these features. What I want you to do is write down, find out what are If you have to calculate this, what all information do you require? Okay. And the second thing which you have not given to me as something which we learned, which perhaps to me was the most important thing that I taught you, was I have been trying to make you understand the physiology behind what the signals matter. Okay. Just now when we studied muscle fatigue, we just spoke 5 minutes ago about muscle fatigue. What did we talk about? We tried to understand the physiology. So that when you understand the physiology of what we are talking about, you can then identify the suitable feature. If you are just playing in the dark, finding some feature and throwing it at it and trying to say this will work or not work, that may work, may not work, but it is not something which is scientific. So for each of the feature that you consider, I want you to make sure that you understand what is the muscle physiology, what is happening underneath. Okay. Sari. Sari is yes, right? Understand? What do you say? Understand? Purazinda. Purida. Okay. Purida. Ah, when did you come? Good. Well, namaste. So, what happened? Are you gonna sing? Huh? He sings? Okay, so what else would you like? Okay. How long? Done? Anyone's looked at something you did? Huh? No? Ah, that's not nice. I had a water bottle first. If I tell you to get RMS of a signal, what do you need? Can a monkey do it? Why not? You just press a button, right? Monkey can do it, or yeah, we need you. Monkey can't do it? Okay, then we need you. Why? What are you going to tell that the monkey cannot tell? Think. Yes, I'm listening. I'm all listening. Like Ganapati is listening. I'm not going to say anything. Interpretation would be, but before you even punch in the button of RMS, you need to do something. What do you need to tell? All right. So you need a window size. Okay, one thing. So one of the examples was that. What do you need? Okay. You need to know the sampling frequency. You need the window size. Know approximately at what frequency is the output. Right? If there is going to be only one piece of contraction, one thing, then you might do it for the whole day. You don't care about the window size. But if the guy is going jogging, maybe it's a different window size. All of those things are going to matter. Okay. Similarly, variance, entropy, PSD, all of these would have their own nuances, own subtleties, which will be important. And you need to understand that. And in order to do that, you need to know the basic physiology of what is happening. Now, this is for strength of the signal. We also spoke about things on muscle fatigue. And what did we talk about? Entropy. Right? Now tell me, we are studying all of these things. We talk about frequency, don't we? What is frequency? Opposite of time. And do you know what is time? Pardon? What is time? No, I'm not saying what is the time. I'm saying what is time? Huh? One factor which is useful to measure anything. I don't understand that statement, but that is me. Anyone else understood what that means? But I am leading you to be correct, by the way. Anyone else? What is time? What is time? Distance. Distance divided by velocity. No, she is absolutely spot on. Have you been reading that book by Stephen, whatever that guy? Okay, another book like that? Possible. I do not know. Now the second question exactly comes. She is raised a question that time is only measured in terms of distance, and distance means space. What is space? Huh? Back.
There is no any.
There is no matter. But even if you consider a molecule, 99.39 later, it is space anyway, right? So matter is really not relevant. But what is space? Huh? In which there is time. Right. So space, time you define in terms of space, and you're saying space is when it's time. Do you understand? How many of you have watched a serial called Big Bang Theory? You know about it? It's a television show. You know that there is a theory called the Big Bang Theory? What does it describe? So initially there was combined. What was combined? So all the universe is combined, but where is the space? Was the space outside this box or inside this box? So space also. Oh, so space is there. So space was there before the Big Bang. So where did the space come from? Right. And she said that the space is only definable in terms of time, in which there is distance. Right? And she's talking about matter. She's forgetting about space altogether. And she's talking about a Big Bang. So if there's a Big Bang, there has to be time, because there cannot be no time and thing. And if there was time, that means there has to be space. That means nothing ever started. And we know most of the matter is space anyway, empty space. So that means there is no time, there is no space, and there is no frequency. Right? It's all Maya. You understand Maya? You in Maya, the Mayavati, Maya. It's all an illusion. Right? Okay? So now, what am I leading you to? The window. Right. Before we even go down that path, the point I'm trying to make you understand is we get so easily sucked in, believing things which are not true, or not at least provable. We believe in space and time, right? How many of us do not believe in space and time? And how many of you have ever thought what is space and time? Maybe never, right? So we live a life where the fundamentals of our lives we do not know, and then we get upset. In this talking about space, we have some time to kill. So because what I planned is do one thing. You see this dot? And you see this board. If this is the Earth, this board is much smaller than the solar system. In fact, this room is smaller than this solar system. Right? Now you consider the universe. And the solar system is kind of what? They would put 10 to the power minus about 70 or something. Now you take that. So of course you might have all the grains of sand and many more, and still you are small. So in this tiny little rock that we are in, and how many years are you going to live? 100 years? How many years is the human race? 100,000 years?
Yeah.
Approximately speaking, 100,000, right? On this little dot for 100,000 years is all the humanity is. And our own existence is not even 100,000 years, it is only 100 years. And we think we are the center of the universe, where everything what we do is important. What I'm saying, what I'm eating, how have I washed my hands? The point I'm trying to make is life is a joke. Learn to enjoy it. You know, yeah, people talk about differences between people, skin color, gender, whatever. Are there real differences? How much difference is real? We cut our hair, the hair goes in the garbage. We don't run after that and say, that's me. It's gone. I drink that water. I go to the toilet. Keeps happening, right? Cycle. Point I'm trying to make was that do your work intelligently, importantly, and whatever. And it's not going to change the world. You know, even if you were the president of the United States, the biggest country on the earth, the biggest bully you might find, Mr. Trump, even he can't do very much. He can cause lots of, dramas, but that's it. Do your work honestly and don't think. And I mean, what Newton wrote was later cancelled by Einstein, and what Einstein wrote was written 10,000 years ago. So things keep coming and going. Our point is, our purpose is that from our little viewpoint, to do things as honestly as we possibly can. There is never going to be one answer. If anyone says there is one answer, then you can tell the person that you are lying. Right? If there's anything, if I tell you that this is the only answer, I'm wrong. Human race is here. Yes, we are consuming more than what we should. We are consuming plastics and air conditioners and everything. It's going to happen. We're going to ruin the planet. Okay. The human race will go away. So what? It's a tiny little rock in the sky. It'll go. The animals will be very happy without us. On that very happy note, I think it's coffee time. Enough of philosophy. We are now in the next session. We're going to be doing some of this. Okay.